Hi, my name's Ian Burgess and I'm going to cover simplified methods in fire engineering. When you stand up as an academic with the word simplified on your title slide, you can feel the waves of skepticism around the room. I wish I had the copyright on some of these photos from Cardington actually, because they get shown at every conference I go to, time and time again. As Walter said, this is the BRE corner test. This is actually the aftermath of the big demo test, where they put the bits of plastic and the old furniture from, I think it was British Steel Swindon Labs at Rotherham into it. So it was a really dirty fire and really hot. And the key facts are down here. When we actually designed Cardington and did some analyses, the best fire resistance we could get for all those unprotected secondary beams was 680 degrees, which actually checked out really well with the Eurocode, which was currently in draft at the time, and with BS 5950 Part 8. And this is the startling thing, of course. 1150 degrees was the temperature that those steel beams got to in that test, without apparently any kind of real failure in the sense of the fire spreading or the building falling down taking place. 1150 degrees, they don't even tell you what the strength of steel is. It's somewhere in the region of 3% of its normal yield. But it's so unreliable testing at that sort of temperature, you don't bother really. Okay, what came out of Cardington was some really interesting observations, because clearly these composite slabs are standing up when all the documents tell you they should have failed. And so there was a bit of head scratching going on after Cardington. Finally came up with the fact that the slabs were holding the beams up. And this is a very simple sort of illustration of the way slabs behave in fire. There's a slab. Initially, you start heating things. You heat the beams underneath. You heat the slabs on top, which heat slower. Thermal expansion dominates, and the slab tries to expand against its environment, therefore causes massive compressions, probably buckles itself downwards a bit. But basically, it's pushing against its environment. As temperatures go up, and they keep going up, certainly in terms of that test at Cardington, everything reverses. In the end, the steel weakening gets so much a dominant effect that the slab is actually hanging there, like the roof of a tent, effectively, against its boundaries. So the middle of the slab is now in a sort of uniform tension. And the wonderful thing that can happen is that provided the edge beams, the boundaries of the slab, are kept fairly close to where they were originally in the vertical sense, you get this rather wonderful ring of compression around the outside. The whole thing works a bit like a bicycle wheel. Bicycle wheels, tension spokes, compression rim. And it's all self-equilibrating. All you've got to do, if you can achieve this tensile membrane action, is to provide the vertical support around the outside. And that's become the basis of various approaches that have happened since Cardington. Number one is, of course, what the really clever guys from industry will talk about later, which is model the whole thing with really clever finite element analysis and see how it all interacts. This is an intermediate approach that I'm going to deal with now. Just one thing to start with, just to illustrate this point about having to support the slab vertically. I always think of the way the slab behaves as a matter of whether you can do origami with it. Can you fold it? Can you do a paper folding solution? If one of your beams, or any of your beams, or all of your edge beams, actually is capable of collapsing, folding plastically in the fire, then in order to hold that slab up, you've actually got to have a whole load of horizontal restraint forces from the surrounding structure. That doesn't work very well, obviously, for edge bays of your building. So this is what we call catenary action, really is a fairly dodgy thing to rely on. This is what happens when tensile membrane action really works for you. You're supplying the required vertical support around the edges, the middle of the slab goes into a nice tension, and the concrete itself around the outside, and maybe the edge beams themselves, which are composite, carry this balancing ring of compression. And that's what both these methods are actually based on. The first thing is that you can buy into a design strategy for your fire protection that says, I'll protect those support beams on the column grid of the structure because I've got to provide this vertical support. But I can very often afford to leave these interior secondary beams, composite obviously, unprotected, sometimes partially protected, depends on the circumstances. Two approaches that came out of this observation and this general thought that you could use the strategy of partial protection of the steelwork was to say, number one, okay, we'll do it and we'll model it fully with whatever software we've got. The software has to represent all the structural actions. It has to represent the temperature distributions and all the things that flow from temperature distributions. Weakening of the materials, expansion of the materials, they've all got to interact with one another. This is what you get if you're trying to use one of the standard packages, the big American devices, Abacus, ANSYS, and the rest of them. You throw a lot of finite elements at trying to model this. At the end, if you're a specialist, you can get very efficient with it. If you're a non-specialist, it takes you ages to actually build the models to do that. The alternative is go for something like Vulcan. I'm not here to advertise Vulcan. It just happens to be the thing that I can get free slides for. But there are various bits of structural fire engineering software which are strictly dedicated to modeling particularly multi-story buildings with fires in various areas of those buildings, and particularly composite buildings. So that makes the input of the model very much easier because you're restricting the scope of what you're doing. SAFIR is from the University of Liège. I have to advertise that as well, really, and is very good. I cannot say it isn't. It's incredibly good. Again, this is just sort of words, and you can read it later if you want it. I suppose it's worth making this point at the bottom here that in technical terms, if you're going to use software to try and model the behavior of building with fires in various compartments, then it absolutely has to have this magic word, geometric nonlinearity, or else you will not ever see the effect of tensile membrane action. Now, there are two approaches really that come out of this general acceptance that slabs can work in tensile membrane action, and that they can provide a considerable reserve of strength in fire to compensate for unprotected steel downstand beams. The first of these, T-Slab, free software, which comes from the SCI. Why would you not download it and use it? I'll tell you in a moment what its advantages and disadvantages are. And in terms of something intermediate on the basis of the modeling software approach, we at Vulcan produce something which is a cut-down version, which effectively allows you to examine what really happens in tensile membrane action within a single slab just the same as you do with T-Slab. This is what you're trying to achieve, of course, which is unprotected beams and protected beams on the column grid line. The economics of that changes from time to time, and at present it's not the most economical thing in the world, removing fire protection, because fire protection is relatively cheap. T-Slab is, as I say, a free spreadsheet. It's an Excel spreadsheet provided by the Steel Construction Institute, and is based on a method developed by Colin Bailey, who was, at the time was working at BRE in about 2000, in the aftermath of all the observations that had happened at Cardington. And it's a rather beautiful method that takes some old research and does a very simple model of the way tensile membrane action works. SCI developed this into a spreadsheet, put some tweaks on it, and it's extremely easy to use. Only works for composite floors of this kind. This is a complex graph. This is where you say, okay, we've got an academic here. But basically, if you look at the black line here, the thing about tensile membrane action is the more the slab deflects, the more capacity it gets. So you can say, I need this much capacity, therefore I need this much deflection. And you can calculate that using Colin Bailey's method, or the spreadsheet will do it for you. Unfortunately, at some stage, you can't let slabs deflect indefinitely. They tend to crack eventually, and the fire gets through, and you get an integrity failure. So what T-Slab does for you is it calculates the level at which that big crack through the slab occurs. And so you've got a limit at which you can't really use your tensile membrane action any further. If it doesn't give you the required time of fire resistance, and you can see here, given you 35 minutes, then you're going to have to do something. You change the position of your reinforcement in the slab, or you increase the amount of reinforcement in the slab, or you change into a partially protected scenario. And these are the sorts of things you need for T-Slab. It'll deal with all kinds of wriggly tin decking. As I've said already, the really critical thing in using it in terms of trying to design something to work in fire is the position and the area, in fact, of the rebar in the slab. If you're simply determined to stick with the anti-crack mesh, then obviously it's the position, because the position will dictate how quickly the steel gets hot. If it's closer to the exposed surface, it's going to get hotter quicker, basically. And the next few screens just sort of show you how easy it is to put the normal structural data for that slab panel with its protected edges into T-Slab. Just the normal engineer's data in the white boxes. The grey ones are just calculated from that data. And so I'll skip through those. Loading here, beam spacings, beam sizes, that sort of stuff there. And you'll notice that, well, the one thing I'd hoped Walter would deal with, which he didn't, although he did talk about how awful this standard fire is going on forever, with the fire brigade pouring fuel into it. The Eurocodes very significantly, Eurocode 1 in particular, 112, has allowed you to, if you know the characteristics of a compartment, and you can negotiate to create a few different ventilation scenarios with your building control, you can actually get a very good model of a natural fire, or a whole bunch of natural fires, which go up and then come down. The fact that they go up, come to a peak and then go down is wonderful, because suddenly you're not worried about 60 minutes fire resistance necessarily. you can have complete burnout. You know, the whole compartment can just burn out and the structure's still standing. So you have infinite fire resistance. And you can have either of those two, or both of them, within T-Slab. That's the results for you that you get out of T-Slab. Over here is what they call a unity factor. I'm never too happy about that term, but sort of inverse safety factor. If it goes above 1, you're in trouble. And here you can see this is clearly a standard fire scenario because the beam temperatures in an hour have gone up to nearly 945 degrees, which is the magic number at an hour. So you're safe with this particular design. But again, if you're not safe, your next stage is you're going to have to do something about that mesh. Vulcan Lite, I'm again going to run through this very quickly. It's finite element. It's a very quick way of creating a slab panel which dumps you into Vulcan and then does a real analysis. It doesn't tell you how much deflection you need, doesn't tell you when the crack occurs. What it tries to tell you is what really happens, given the fire that you've put in. Obviously, just an illustration to say, you know, slabs need a lot of layers in fire analysis because the temperature's got to creep through, and all the things that flow from that temperature creeping through have to happen. That's what you'll get out of Vulcan. Slightly misleading here. Here I totally disclaim this slide. Roger Plank, dear colleague of mine, put this collection together, and this caption here is just wrong. It's not linear slab. Linear slab will do something totally different, and you don't want to know. The individual member, if you were just testing that composite beam, would indeed do exactly that. It would zoom off into the distance and run away, hit the deck. You've got real failure. In terms of having a slab panel with protected edges, you can see that you just meander on downwards, slightly increasing your deflection as temperatures increase. Eventually you will get to something that genuinely causes a runaway. This is the sort of data you would put into Vulcan Lite. You can put in the necessary data to get you a parametric fire. Remember I said Eurocode model of a natural fire. Or you can put in a BS 476 standard fire to whatever heating period you like. And you can even put some cooling on the end of it. Define a slab. Slabs in Vulcan Lite don't have to be rectangular. People keep telling me that real buildings don't have rectangular slabs all the time. Can't imagine it myself. But they just have to be quadrilateral. But you can have what you like in that sense. And then you put secondary beams into it, whatever direction you like. Select their sizes. Put fire protection to various specifications. You can either put it in as a generic fire protection material, passive protection material. Can't do intumescence. There's just too much secrecy in intumescence. Or you can put it in just as a protection period, in which case it will guarantee you get to the right temperature at the right time. Spanning direction of the ribbed slab, because the slab itself can be treated using the different sort of stiffness properties in both directions. And finally, you stick on your fire limit state load. And that's what it creates. It dumps you into Vulcan. And you do the analysis, you hit the analyze button, and it gives you results, which that's just the standard curve. That's just the maximum displacement. You can have whatever outputs you like. I don't think I've left us time really to read all this stuff, but it can dump your results into Excel so that you can play with them later. Just going to just let this run. It's an illustration of what actually you could animate within your whatever finite element model you use as the fire increases. And that's an area of slab with clearly four protected panels, which is behaving perfectly respectably. One of the nice things that you can do, I'm not going to explain this particularly, it basically represents the forces in the concrete slab. But you'll see, as I let the temperature of the fire increase gradually, you can see those forces in the slab changing radically. And when it gets to, we stopped it at 900, you can see that the stuff in the middle has all gone red. That's your tension area of a tensile membrane action scenario. And round the edges of each of the slabs, you've got these all aligned parallel to the edge, blue lines, quite large blue lines, which actually do give you, quantitatively, your compression ring around the outside. So you can actually confirm for yourself, just qualitatively, whether the tensile membrane action that you're aiming for is actually happening. And to me, I don't like tables and numbers, but I love stuff like this because it gives me a hell of a lot of confidence. One of the other things you can get out of a software approach to doing this is that you can get the forces that are being created in your beams. Clearly, one of the major effects, which people don't emphasize enough, but one of the major effects, if you look at it in any depth, that happens in a fire, is that various parts of the structure expand at different rates. And that can cause huge either compression or tension forces in the steel members, either protected ones or unprotected ones, because you've got to have equilibrium between things in compression and things in tension. And the clear corollary of that is that the connections at the ends of the beams, especially those that are being pulled where the members are in tension, have to be made to resist those forces. They either have to be made strong enough or they have to be made ductile enough but that's advanced stuff. But let's just say the connections need to be made strong enough to carry the tying forces. And Walter showed you a few of these from Cardington, actually rather better focused than these. But you can see what happens particularly in the cooling phase to fin plate connections there, just slices through the bolts. And here, this is the one where you had a partial depth end plate. Again, it's in cooling, I admit it. So the only people that are heavily interested are the fire brigade, usually. And actually, it's sliced through the heat-affected zone on one side only, which was rather a nice result because the other side kept the beam supported. Thank you.